Alright, CNT125, Chapter 11, we're on the section on availability. So availability is how consistently and reliably a connection system, router, switch port, whatever, can be accessed by authorized personnel. So your network functioning, running, people are able to get to the server, get to their files, get to their login, log into the network, whatever. That availability is usually expressed as some kind of percentage. And a lot of times the slang gets used as the number of nines. You know, we're a 4-9 shop or a 3-9 shop or whatever. And what that means is 4 nines is 99.99%, 3 nines is 99.9%. That's usually maybe kind of a slang term that people use. And what that turns into is a 99.9% available facility. Every day there's, average minute and a half, if you will, of downtime, which by the end of the year equates to 8 hours 45 minutes. So almost an entire day of things not being available. Depending on the facility, that might be okay, that might be tolerable. Other places that may not be tolerable. So that's what they talk about with availability, usually a percentage of how available things are, how much downtime there is. There is an uptime. Most devices, whether it be servers or that sort of thing, we usually have an uptime indicating how long this has been functioning and working. That would be maybe something you're checking on for availability of system. This is actually an uptime on a Microsoft system. Here on a Linux system, you can just actually use the uptime command. It tells you how long it was open. Actually, I just booted the Linux VM to get that. It was only up for 2 minutes, but you get the idea. You can do uptime on it. It tells you how long it's been functioning or running. Fault tolerance then is, okay, so if we have things really available, we're probably doing things to make it fault tolerant so it is available all the time. If things are not as available as we want, these would be some things we'd want to do, some fault tolerance things we'd want to do to get our availability up, things more functioning. So fault tolerance is just that. How capable is your systems and network of handling outages or faults and keeping things running? So if we have a hard drive failure, is there other things in place to be having copies of that data so we have not lost it? If a server power supply goes, do we have another server power supply running that immediately kicks in, or do we need to actually get one and plug it into the system? That's what we're talking about with fault tolerance. Failure then is when you do have something deviate from a normal performance. Car breaks down the highway, that's a failure. The fault is actually the component, if you will, that probably caused the failure. So if we use our car analogy, the water pump breaks, that is actually causing the car to break down. That's what has caused it. So failure and fault, a lot of times, people think of them synonymous. In IT world, you kind of separate them. Fault is usually the thing that might cause a link to go down. We had a router port fault that caused the link to fail. Okay, just to kind of, it seems like we're splitting hairs, but that's usually how they define those. Your fault tolerance system goal is to prevent the faults from becoming failures. So using our fault example before, if we have a router port go down, is there something else in place to take over or route the traffic? If it is, okay, the fault of the router point going down, that is a problem. However, it has not caused an entire site to lose their connection because we have another link there online routing the traffic. Okay, if you kind of get the idea behind that. So you might have a fault that because you planned for it, it does not become a big failure, and things are going to happen. So the whole idea behind this is to try to engineer for that. They also bring up two terms at this point: MTBF, mean time between failures, and MTTR, mean time to repair. So mean time between failures is a average rating of how long you expect something to function before it might fail. And we're doing it's a lot of predictions, but if you look at things like, I just pulled up some Cisco router model numbers, 2960, switches, Cisco switches 2960. The mean time between failure rating for these is 233,000 hours, if you will. that gives you a ballpark to realize, okay, that turns to how many months and how many years that might factor into your replacement schedule of gear. Okay, we're going to do a 3-year replacement of gear and so forth. You're trying to replace things before you get to the point of like they're going to fail. They're at their end of their life. Okay. In the meantime, to repair then is how long it takes to, if that switch fails, bring a new one online and put it in place. That is something that a company would work on. It's like, okay, can we tolerate taking a day to put a new switch in, or is that something that needs to be done within minutes, if you will? And again, that would need to be planned on. So redundancy is the name of the game. Redundancy is the name of the game. Do we have something in place that will kick in automatically or be able to replace or step up almost automatically? The con for all this is going to be cost. And again, each facility, maybe a school district, it's not too critical to have redundant switches. We can replace one, etc. It's okay if it's down for a day. We'll replace it. We'll get things back online. But a place like a hospital may not be acceptable. So there, you might be planning to have replacements ready to rock and roll or configured and ready and in place and ready to roll. So the idea with redundancy is you're trying to eliminate these single points of failure, trying to make things more available, high availability of our links and our systems and our devices. So to give you an example here of, a network where you have a switch connected to a router, connected to a firewall, connected out to the ISP using a signal T1 line. This might be a map of a small branch of a company. That's relatively normal. But if you look at that, you have lots of single points of failure. So a solution could be literally having some redundancy built in, 2 ISP connections and 2 sets of gear, some with links between. The obvious benefit of that is if you have a link or a device fail, there's other ones in place ready to rock and roll. The obvious downside to this is cost, and that would need to be a justification for the company. Does it justify us having all of this equipment bought, installed, running, maintained for a redundant connection, if you will? In some places it would be quite justifiable. Other places it would not be. So our utmost fault tolerance is when I actually have critical devices that are set up to be automatic failover. So I might actually have, as we said right here, if I have these 2 connections, I might actually configure these to work in tandem, that if one fails, the other one's there automatically already running. So router NIC fails, other router NIC can automatically handle the first NIC's responsibility. Yep. If you don't have if it's impractical to do that, I might actually have something in place where I can do some hot swappable parts. If it's not practical to have that router there running all the time, maybe I just have it sitting on the shelf configured and ready to go, that I can pull the bad router out, put the new one in, or pull the faulty port out and put the correct port in and reboot, and we have minutes of downtime, if you will. And that leads us to the hot spare, cold spare. Hot spare is basically ready to rock and roll for the failed part. The cold spare is maybe one sitting on the shelf ready to put in place, and I bring it online and copy the config over. So I might have, an hour of downtime versus minutes of downtime kind of thing. Another way to handle some availability issues is some redundant links. We looked back there about having redundant links to the ISP. Well, I can have redundant links between devices, whether it be routers, switches, or router and firewall, firewall to ISP kind of thing. I can have some redundant links. So what I can do is some what's called link aggregation. I actually have maybe 2 ports connecting to something, and I configure those ports to work as if they're like one. So I might have 2 switch ports connected between. I have 2 switches and I have 2 switchboards connected between each of them. I can have those all act as like one giant cable. So if I have one fail, the other one's already there running. I might lose some bandwidth, but I at least have a connection. Different devices call it different things. Some call it port aggregation, NIC teaming, bonding, bundling, Cisco's Ether channel. You might see this go by another different names. However, it's the idea of taking 2 links between something and make it act like one giant link. The advantage of this is actually total throughput. So if I have 2 gig links between switches, I've now increased my throughput to, if I have let me say that again. I have a gig uplink between my two switches. If I use both of those, I now have a 2 gig link between my switches. Nice, I've added some bandwidth. The other advantage is it's automatically failover. If one of those fails, okay, I've gone back to having a 1 gig link between them, but at least it's already there and functioning. I don't have to like recable things or reconfigure things. And I can also many times configure them to load balance, where it's using both. Please use both. Don't make it sit and standby. Please use both and have them share the data across both of those links. And here is an example of, I have a switch connected like so. I could configure these 3 ports. Normally, STP would shut down the redundant links. If you think back and remember, STP would shut down those redundant links. Well, I can tell the switch, please don't do that, and use all 3. So if I have an issue with one, the other 2 are still there and running. Very, very beneficial. Very beneficial. It's increasing our bandwidth. And here's another example between, switch and server. I could actually have 2 NICs in my server and have 2 links to the switch and have that act as one giant link, increasing my bandwidth to my server. Now, to do that, usually protocols, some sort of protocol or some sort of configuration needs to occur so the switch understands what's going on. And they often use LACP, Link Aggregation Control Protocol, initially defined by IEEE 802.3AD, currently defined by IEEE 802.1AX. Okay, whatever. But that protocol is there to communicate between the switches. Hey, is this a link we should be sharing on? Yeah, okay, great, sounds good. And that's what that's all about. And you can actually configure them to be static, passive, or active. They're both manually configured if you're doing static. Passive is one it's listening for. Active is like, hey, I'm going to try to make a link with you if I see another one show up. Let's do it. Okay. So here will be a sample config of a switch. Actually go in and indicate these 2 ports and say, okay, switch port access VLAN 1 native VLAN, channel group 5 mode active. And what it ends up looking like, I have my packet tracer here. Let me pull this guy back up. I'm now going to actually look at, I'm actually going to look at the switch link here. If you'll notice, I actually have 2 cables connecting from this switch, to this switch, and I'm using the 2 gig ports here and the 2 gig ports here to connect them. So I'm going to open up this switch now just because it's a little cleaner config. If I look at the CLI on this guy and do a show run, what I'll see is, get out of here. There we go. I come down here on gigabit port, Gigabit Ethernet 01 and Gigabit Ethernet 02, switch port mode access, channel group 5 mode active. What it's doing is making the Gigabit 1 and Gigabit 2 ports act like one giant trunk link between the 2 switches. So these two gig links are now making a 2 gig link between my switches, but more importantly, some redundant links. If one of these fails, the other ones are already configured and running. Yes, I would need to go fix it and repair it, but at least it's still running while I'm trying to fix and repair. And I don't have people screaming, hey, connection's gone, can't get to the server, etc., etc. That's a way to get some redundant links. Really, really valuable. Load balancer is actually a device that will do that kind of thing for you, send data on each link. Okay, and sometimes you actually see that on maybe a WAN link or an ISP link where traffic's coming into a server. You might use a load balancer to send data across 2 links to the server or server ports. You often run into clustering too. You might actually have a couple servers working as a group to respond to people's requests from the internet. On that cluster of maybe 3 servers, the outside world sees as one, but they're all configured to run kind of in tandem with each other. So if one fails, okay, we don't have as much throughput as we did before, as much response, but I still have web servers running and responding to people's requests or orders or whatever happens to be. Very common to do. To do that, you end up using some protocols like HARP to be able to have people, outside people, respond to that as if it's one node. And I think out here I have an example of just that. Here is 2 routers acting in tandem. In this case, this is hot standby routing protocol. 2 routers acting in tandem. A node is going to see these 2 routers as one IP. And if one fails, okay, great, it's going to use the other one, in this case, to get out to the ISP. So your hot standby routing protocol, CARP, all those are going to work with redundant links and have everybody see it as one IP.